Welcome to the Jack Westin MCAT podcast with your host, Phil Hawkins.
And Azaii Muñiz.
I am excited. It's Physics Day. Those of you who know me know that I am a physicist at heart, despite going to med school, despite the biology PhD work. Really, I love physics. And today we're going to talk about the father of all physics and the foundation of most physics that you're going to see on the MCAT. And that is Newtonian mechanics or Newtonian physics. I feel like that sounds really big and complex, but really it's just pretty much most of the physics that you deal with. There's some stuff that is outside Newtonian physics. The MCAT kind of starts to touch maybe on a little bit of these, but the vast majority, 99% of the stuff you're dealing with on the MCAT is Newtonian in nature. So pretty excited about this overall.
I would be shocked if you were not excited about today's podcast episode. I think that would be concerning for all of us listening. Mm-hmm. But yeah, so like you said, Newtonian physics is a good chunk of physics on the MCAT. And so it's important to think about when it applies and then also the cases when it doesn't apply, which you already hinted at. And we're going to talk about, the main rules and whatnot, but similar to how when we were talking about the ideal gas law, we were like, it doesn't apply under these conditions. Newtonian physics is most of life, but if something is really, really tiny, we can't observe what we're hoping for, right? Or what the information that we need, it no longer applies. Also, if something is going really fast, so if we're nearing the speed of light, for example, Newtonian physics starts to break down. And so we can't apply it in that case either. Like you said, we're not going to be doing a whole bunch of that on the MCAT, which saves us a lot of headache. But quantum physics is when things are really tiny, which you will see a little bit of. And then if it's super fast, it's relativistic physics. And random kind of thought, there was on NASA's website, they have this mini education page, and it's really kind of cute. It's not, I find it adorable because it just makes sense for me. And if it makes sense for me, I feel like it'll make sense for a lot of people. But they touch on a lot of what we're going to be talking about through the lens of rockets, right? And whether or not things apply. And so they occasionally talk about speed of light, right? Because those are things that they think about. But it's just really a really fun page to just kind of take a peek at. I don't know if you'd ever seen it, Phil.
No, I haven't. I feel like I'm going to have to go check it out after this because I definitely want to take a look.
Yeah, they have this video on the first flight and the airplane. It's cheesy, but it's really nice to think about. Yeah.
I feel like Newtonian physics is it makes sense. It's fairly intuitive to people. You start going really fast, with the relativistic, or really small. Like you said, things kind of break down. The rules change, right? If you go really small, all of a sudden something could, in theory, exist in more than one place at a time, which is how does that work, right? That doesn't work if we think about tennis balls. This tennis ball can't be over here and over there, right? It's got to be in one spot. Really, I feel when you start thinking about those fringes, right, the relativistic and quantum, all of a sudden your brain starts to melt because it doesn't make sense, because we tend to view the world through the lens of Newtonian physics. And so we tend to understand that with relativistic stuff. If I have a car and I put more energy into that to make it go forward more, the velocity speeds up. Or rockets, right? You burn more fuel, you speed up faster, right? You push something, it picks up speed. But if you're talking about things that are already going very fast, approaching the speed of light, if you push something, it doesn't actually go that much faster. What happens is time slows down and space distorts and dilates, and it melts your brain if you think too much about it. One of my favorite things that I learned about was space dilation and time dilation in physics, where if you had a stick that was 15 foot long, if you made it go fast enough, it could fit inside of a room that was 10 foot long. And so the stick is longer than the room, but if the stick is going fast enough, it'll fit inside. And that doesn't make sense, right? When we think about the world of Newtonian physics. And that's why it's really important to just kind of like help us understand what is the realm of Newtonian physics. Like if you throw a baseball, a car gets into a wreck, you have a rocket going to space, an asteroid collides with a moon, right? All of those things are going to be like handled by Newtonian physics. And so when we say the vast majority of things, we really mean that, right? Like unless you're talking about like the Higgs boson, or you're talking about, something going the speed of light, then outside those scenarios, it's pretty much all relativistic or all Newtonian physics. Side note, just as a super interesting thing, like Einstein obviously figured out the relativistic physics stuff, but he spent like the last several decades of his life just trying to figure out how both of those things can be true, the relativistic and the Newtonian, right? Trying to come up with a unified theory to explain how the entire universe works. Because right now, basically, we have a toolbox that works for things going really fast, a toolbox for things really small, and a toolbox for everything else. And everything else is Newtonian. And so all of a sudden, all the equations here don't apply in that scenario, and they do apply in this scenario. And a lot of physicists really want to have this grand unified theory. And so that may be something you may hear about just in the world, like a unified theory of physics. What they're talking about is trying to make sense of like, how do all three of these things exist at the same time? Quantum, relativistic, and Newtonian. But I feel like we've zoomed out a whole lot, and like I'm just really excited and interested in like, how does this work? Because you think too much about it and your brain turns to soup. And I'm like, I don't understand relativistic theory. I kind of don't know if anyone does other than Einstein to like conceptualize it. But Newtonian stuff, like Newton was the first one to kind of come up with a lot of these things. Which is why it's called Newtonian physics, after Isaac Newton. And he came up with 3 laws that helped us understand the universe and the rules of Newtonian physics. The first law, and I want to be clear, you need to know all 3 of these laws, and it's probably worth knowing which one is which, because the MCAT could, in theory, say, according to Newton's 3rd law, or according to Newton's 1st law. And so you need to make sure that you not just know these laws, but you know which one is which. So the first law says objects in motion will stay in motion, and objects at rest will stay at rest unless something exerts a force on it. So if you have something that's moving, it's just going to keep moving until something pushes on it. If you have something sitting still, it's not going to take off unless something pushes on it or pulls on it, right? So objects at motion or in motion will stay in motion. Objects at rest will stay at rest unless there's another force acting on it.
Yeah, I once heard this example of like a hockey puck on the ice because it's darn near frictionless. And so on a really like well done ice rink, if you send that hockey puck, right, it's just going to keep going, and then something else has to stop it. Hence, you stop it with the hockey stick before it reaches the goal. But the idea there is that if nothing else is acting on it, it's just going to keep doing whatever it's doing, right? Yeah. And so sometimes we are sitting down and we're just like, man, unless something gets me out of my chair today, we're stuck. So obviously that's not literally the case, y'all, but the idea being you need something else to cause movement. And that's where Newton's 2nd law comes into play. And it's that any given force is equal times the mass of the object multiplied by the acceleration. And so that's for any given force that's acting on an object. But we also know that something can have a net force. And the idea being that any addition, right, or subtraction of the forces acting on an object are capable of producing motion. And so if something has a net force acting on it, like us having a net force, we have a motivation to get up, right? Then we're going to produce a change in that motion. Or, the hockey puck, when someone hits it with the stick, right, that stops it. And so instead of just continuing its motion, there is an end to that particular motion. There's now different forces acting on it. And so with the 2nd law, it's the key there is you know the basic equation. And the really cool thing is as you go through Newtonian physics, and as you talk about forces, there are different equations that you can use, but they all come back to the same force equation. And so they're just different iterations of the same thing.
Yeah. This is a super high yield equation, like F equals ma. Force is equal to mass times acceleration. And you're right. Well, the thing is that force could be a normal force, a buoyant force, an electrostatic force, right? It could be a force of like contact with like a hockey stick hitting a hockey puck. I do want to say a lot of students, there are some students that get kind of tripped up by a little bit of the first law. They think that like, well, if I throw a baseball, it's going to slow down as it's going through air, and like there's nothing acting on it. And so why is it slowing down? But like there is stuff acting on it. It's drag, right? If I went to outer space and I threw a baseball, it's just going to keep going at the same speed forever in that case. And so that's the first law. But something that's kind of interesting is Newton's second law actually kind of explains the first law in the equation, because F equals ma. So if we have no force, then we have no acceleration, because F equals ma. So force is equal to the mass times the acceleration. If force is zero, acceleration is zero. So if you have something that's not moving and there's no forces on it, it won't accelerate, which makes sense. You have something that is moving and there's no forces on it, it's not going to change its speed. It's not going to accelerate farther or decelerate. So like objects in motion stay in motion, objects at rest stay at rest. Newton's first law, unless there's a force acting on it, is really just saying like, oh, when force is zero, acceleration is zero. Then Newton's second law kind of says that exact same thing, where force is equal to mass times acceleration. So force is zero, acceleration is zero. I always felt like Newton kind of phoned it in a little bit. Like the first law is really just like a specific application of the second law. And so like really there's only two laws, and he just got kind of like lazy and tried to make it longer, like myself in high school writing an essay. I'm just like, I'm gonna pad this out a little bit. But like that being said, it is still a worthwhile kind of specific case to understand. And to be honest, that was not something that everyone just automatically understood. Before Newton, there were physicists who thought everything kind of wants to stand still. And so things will always slow down no matter what. But like that's only because friction and drag in general tends to make things slow down. But the F equals ma stuff, this gets tested a lot, and I could see the MCAT doing some really specific, questions about like what happens if we have two objects that both have the same force on them, but their masses are different. So when that happens, whichever one has got the higher mass is going to have a smaller acceleration. And so like another way to phrase this is like heavy stuff is hard to slow down or hard to speed up. This gets tested a lot in like some really applicable things. I know in one of the section bank passages from the AAMC, there's a passage about MALDI. There's also like how a mass spectrometer works. I know I talk about this in the course, but that is also using the same idea that the heavier things are harder to turn. They're harder to slow down. And so if the forces are the same, the higher the mass, the lower the acceleration. If you want a real world application of this, so I have a Great Dane. And if I'm walking my Great Dane and I'm also walking a Chihuahua, if I pull with all my strength on the Great Dane, it hardly moves. If I pull with all my strength on the Chihuahua, it's going to like the same amount of force. The Chihuahua is going to go flying across the yard, right? In that case. And so it's the same amount of force in both cases, but the one with the bigger mass has a smaller acceleration when you pull on it. It would also be the same as like kicking a tennis ball versus kicking a bowling ball, right? Like the bowling ball is not really going to speed up and take off. You'll probably break your toe also, but that's a side thing in the physics. But like the tennis ball is going to take off and go really fast. Or hitting, if you don't want to break your toe, you can imagine hitting a tennis ball with a bat and hitting a bowling ball with a bat, right? The bowling ball, I don't think anyone can hit a home run with a bowling ball, like knock it over the fence. Like that's not going to happen because it's so heavy. It's really hard. Like it requires so much more force to get that thing to accelerate.
Yeah, as poor Chihuahua.
Yeah.
As you were going through and talking about the dogs, I was actually also thinking of a bowling ball, because I think that's a lot more intuitive for us. And so It's also like if you're moving boxes, if you're in the process of moving, it's easier to get the box. I don't know about you guys. I had this thing whenever I was moving, I would put the boxes on the floor and I would just push them and run with it. And so, there are other forces, there are forces at play there that are working against me being able to move that box. But it's a lot easier to do that when the box is heavy than when the box is small. Sorry, other way around. It's a lot harder to do that when the box is heavy than when the box is small. And I think that it can help to also, and I don't know that we've necessarily said this explicitly, but it can help to understand that. And acceleration is just the change in velocity, right, over some change in time or some period of time. And so if we can picture it that way, right? Oh, I can go faster, I can speed up more when something is small versus I can speed up less when something is larger, can be another way to think about this that can feel a bit more intuitive.
Yeah. Also, just like side note, this is, I recently had this discussion with my daughter who is learning to drive. I'm like, you got to be really careful around semis because they cannot slow down as well as a motorcycle can. So you want to give them more space, right? They can't speed up as much either. Like if you pull up at a stoplight and you've got a semi on one side and a motorcycle on the other, like if you're in a drag race, the motorcycle is going to take off way faster because it's so much lighter. And so the smaller mass means that if they all have the same force, the smaller mass is going to have a much higher acceleration. And so that's why motorcycles accelerate faster than cars and cars accelerate faster than semis. It has to do with the mass and like Newton's second law, just the idea that the higher the mass, the lower the acceleration is going to be.
Yeah. With semi-trucks, not only do you give them more space behind them, you do not cut them off.
Yeah.
Do not cut them off because they just can't stop as fast.
Slow down.
So
yeah.
Other life lesson there.
Yeah, for sure. My dad is a farmer, and so we drive semis around. I probably shouldn't advertise this, but the first vehicle I ever drove was a semi. And it was, I was like 13 or 14. But like it wasn't on roads. It was like in the fields, like pulling up so my dad can like, put the corn and stuff in the back. But yeah, first car I ever drove, semi, jumping straight to hard mode. But yeah, so that is Newton's first and second law. Newton's third law is one of my favorites for, I don't know how to phrase this. Like it's one of those laws that everyone knows, but nobody understands it, right? It's up there with E equals MC squared. Everyone knows that equation. Most people don't know that that's the equation for mass defect, which is something that is MCAT testable. And we're going to talk about that in a future episode. We've already planned it out. But the Newton's third law says every action has an equal and opposite reaction. Everyone knows this. But whenever I ask students questions about it, I'm like, okay, if there is something like if I have my food sitting on my plate, and so I set a plate on the table, there's forces pulling up and pulling down on it. So let's talk about gravity is pulling down on the plate. What does Newton's third law tell us, right? 99% of students are going to miss this question. They're going to say, oh, well, then the normal force is pushing up on the plate, and those are equal and opposite. And this is why it's tricky, because yes, that is true. The force of gravity is pulling down on the plate, and the normal force is pushing up on the plate. And those are equal and opposite forces, equal and opposite reactions, or they're equal and opposite forces. They're not reactionary forces. They're not equal and opposite reactions. And everyone gets that mixed up because they're like, wait, what? Like, how is that not what Newton's third law is telling us? The thing with reactionary forces is they have to be the same type of force, and they have to be between the same objects, right? So like if I saw a Volkswagen and played the game I always played with my childhood friends, and so let's say I'm in my car riding around with my friend Tyler, and I see a Volkswagen Beetle and I slap him because it's slug bug, and like that's how you play the game. And so let's say I slapped him across the face. My hand is hitting his face. his face is also hitting my hand. And so his face is going to be hurting, but so's my hand. Now, those are reactionary forces because one is the force of my hand on his face, and that's a contact force. His face is also hitting my hand, which is also a contact force. So those are the same types of forces, and it's hand to face to hand, right? If you look at the table or the plate on the table, right? What is actually pulling down on the plate? It's not the table, right? That's not what's pulling the plate down, right? Because like if I took that table and that plate and I went into outer space and then I set the plate on top of the table, like it's not going to be pulled down into the table. I mean, it will, but like very minutely. I kind of want to asterisk that, but you'll have a very, very, very small gravitational force pulling them together. But here on Earth, what holds your plate down is gravity, specifically gravity from the Earth. And so the Earth is pulling down on the plate with gravity. Gravity is the force, right? And so the reactionary force has to be between the same two objects, the Earth and the plate. And it's got to be the same type of force. It's also got to be gravity. So if the Earth is pulling down on the plate, then the plate is pulling up on the Earth. Those are reactionary forces, right? And so those are going to be equal and opposite. Now, a lot of students like, wait, like the Earth doesn't move, like the Earth isn't being pulled up by a plate. Like it is being pulled up by the plate. But remember, the bigger something is, the harder it is to accelerate, right? It's like if I tied a rope around like a yacht or tied a rope around like a cruise ship or an aircraft carrier, right? If I was trying to pull that, it's not going to move. I am still pulling on it, right, with my rope, but it's so big and so heavy that it's going to be hard for me to accelerate. And I mean, the Earth is way bigger than an aircraft carrier. Kind of, if you think about it, the Earth is the biggest aircraft carrier because there's aircraft parked on it, but it is the biggest object. And so if I were to tie a rope around the whole Earth and pull it, like it's not going to move. But so that plate is pulling up on that Earth, but the Earth is just so large and so heavy. And this actually goes back to Newton's second law. The bigger the mass, the smaller the acceleration. That mass is ginormous. And so the acceleration is like zero in that case. So those are going to be reactionary forces. And so just because forces are equal and opposite doesn't mean that they're reactionary forces. And that always trips people up because in that scenario with the plate on the table, yes, the Earth is pulling the plate down, the table is pushing the plate up, and those are equal and opposite forces, but they are not reactionary forces because reactionary forces have to be between the same two objects, the same type of force. Does that make sense? Do you have anything? I kind of want to go in and talk about the normal force on that because it's a weird thing, but I feel like I've been talking too much and I got too excited.
No, I love this. This is honestly one of my favorite ones as well. What I do is I have students like put their hands on their legs and then name all of the reactionary forces and all of the forces that would apply, the third law would apply to, because it's really similar to the book, right? We often, we forget that it's, and I think we forget that it has to be A on B and B on A. Mm-hmm. And that's really what it comes down to, right? So I should be able to write A on B, my feet on, or like you said, the Earth pulling down on me. So gravity from the Earth, and then B on A, me on pulling on the Earth. And so the same thing is going to apply to when you are sitting on the chair. Same thing is going to apply to your feet on the floor, right? Same thing is going to apply to your hands on your legs. And so I think recognizing that it's not between the Earth and also the chair and the Earth, right? But it's not the chair and the Earth and me and the chair, which is essentially what you were describing. But I really do think that just A on B equals B on A. Well, the force of A on B is equal to the force on B on A in the opposite direction. I think that feels most clear to understand.
Yeah. So I love the idea of like continuing to just break down and pair these out. And so there is like, I think just really understanding this is critical and like breaking these things down. It's like let's look at that normal force of the table pushing up on the plate. There is a force there, and that is pushing up, right? So what's the reactionary force going to be? Well, the table is pushing up on the plate with a contact force, which means the plate has to be pushing down on the table with a contact force. And so like they're both pushing on back and forth on each other. And this kind of seems weird, but let's flip this around a little bit so people can understand this a little bit better. Like if I was laying, so let's say instead of a table, it's me. And instead of a plate, it's you, Azaii. So like if I'm laying on the ground and then you step on my stomach, right? Or you step on my chest, gravity is pulling you down and I am pushing up on you. Like the contact of like your shoes on my body is like pushing you up, right? And so you are being pushed up by me. But I feel it, right? When you step on me. And like in that case, I'm as hard as I'm pushing up on you, you're pushing down on me. And so they're smashing against each other. It's the same thing with the plate on the table, right? The table is pushing up on the plate and the plate is pushing down on the table. Now, those forces are equal and opposite. And so it's a reactionary force. And so like the plate on the table on the plate, reactionary force. The earth pulling down on the book pulling up on the earth, those are reactionary forces. Now, in the case, if you look at just the plate, right? Yes, gravity's pulling down on it as hard as the table is pushing up on it. So those are equal and opposite, but they're not reactionary forces. The other thing I want to note there is that those are the only two forces acting on this plate, and they're equal and opposite, so they cancel out. So there's zero net force, which means there's zero acceleration. So that's going to like Newton's second law, right? Because F equals ma. Newton's first law says, hey, if there's zero acceleration, it's not going to move. And so the plate's just going to sit there on the table. It's not going to take off.
No flying saucers.
Right. But we could change this scenario, right? If I grabbed the legs of the table and I pushed up on the table, right? All of a sudden, gravity hasn't changed, right? The earth is pulling down on the plate with the exact same amount of force. And the plate's pulling up on the earth with the exact same amount of force. That hasn't changed. But now the table is pushing up more on the plate than it was before because I'm like pushing up on the table. And so as a result, the shoving up on the plate has increased. The normal force has increased, which means the plate is pushing down on the table harder, right? To like go to our analogy before, like if you were standing on my chest and somebody else grabbed we had people grabbing my arms and legs. If they lifted me up really quick, like I'm going to feel like you're shoving down on me more because I'm pushing up on you more in that case. So in this case now with looking at the plate, when we like lift the table, the force up has increased. So the normal force has gotten bigger because the table is pushing up more on the plate. So they're not equal and opposite anymore. The force down of gravity is unchanged. The force up, the normal force, has gotten bigger. So this is how you know those are not reactionary forces because they're not equal and opposite anymore. They can be equal and opposite, but they don't have to be equal and opposite because I can like do stuff to the table and make them not equal to each other. And so note in that case, there's a net force up, which means it's going to accelerate up. And that's why the plate lifts when I lift the table. And so I think just kind of like thinking through these and kind of understanding that sometimes we have equal and opposite forces, but that doesn't mean that they are reactionary forces. Like if you look at like a basketball floating in the ocean, gravity's pulling it down, buoyant force is pushing it up. Those are equal and opposite if it's just sitting there floating, but they're not reactionary forces because one is like the water pushing up on the ball, and one's the ball pushing down on the water. Those are reactionary. The earth pulling the ball down, the ball's pulling the earth up. Those are reactionary. But like the buoyancy and the gravity are not reactionary, even though they may be equal and opposite.
So first, I would not step on you, Phil.
Yeah.
But I think the
not
other
even
one
for
that
science.
And I always,
I said not even for science.
Not
I'm
even
okay
for
with
science.
it if it's for science.
I don't want anyone having to end up at the doctor's office.
Yeah.
But yeah, so I think that one of the things that I personally really struggled with that ultimately knowing and better understanding Newton's third law helped me with was kind of the elevator problem. And like you were describing, if similar to how if I were standing on something and it were thrown up into the air, right? That something would feel like I was pushing on it harder. And so it's the same thing with the elevator. It's like when an elevator starts moving up really fast, right? If you have a scale underneath you, it's going to look like you weigh more. You don't, son. You didn't suddenly eat, 10 cheeseburgers on your way up to the 10th floor, right? But since you have something pushing up against you now with an increased acceleration, you're going to push down and going to match it. And so I think that can also be helpful for understanding this. This is and I don't want to go too far down this rabbit hole, but this is the basis also for when we're drawing free body diagrams. So free body diagrams being I draw an object or a set of objects that may be in contact with one another, such as a box on a ramp. You will see that a lot on the MCAT. Mm-hmm. And I'm going to write down all of the forces that apply to a single object of interest. So I'm not, if I have a box on a ramp, I'm not going to sit there for my free body diagram and draw all the forces on the box and all the forces on the ramp, because that's going to get too complicated. And I'm assuming that the ramp is just doing its thing, right? What I will care about is all of the forces acting on the box. And when I add up all of these forces, like you were talking about, Phil, I will know whether it's going to move or not. And that's because it may or may not have a net force acting on it in the direction of whatever that movement is. Same if I just have a box on, the ground and I'm showing that someone's pushing on it. I have to decide, okay, what forces are acting on the individual box and how does that affect the box's tendency to move or not move, which essentially is applying all three of Newton's laws, but primarily that second law, which is force is equal to mass times acceleration, and that net force is the culmination of all of the forces acting on it. So really that second law is incredibly important to know because it will get tested in a bajillion different ways in the physics section of the MCAT.
Yeah. I also want to point out, if you ever do that sort of thing where you're looking at one object and all the forces acting on it, none of those will be reactionary forces, like Correct. No pairs of those, right? Because if you have a box on a ramp and gravity's pulling it down, the ramp's pushing up on it, a rope is pulling on it, right? Those are all things that are working on the box, right? And so other, the reactionary forces are going to be the forces that the box does on everything else, right? And so if all the forces just acting on one object will none of those will ever be reactionary forces. That's a good thing to keep in mind because the MCAT, like I said, the MCAT knows students get tripped up by this. I think this is in the top 2 most commonly known equations that people just don't understand and think that they do, which is interesting. So yeah, just have to be careful. Just because forces may be equal and opposite does not make them reactionary. I know I've hammered that a lot, but I see this all the time. And as a result, the MCAT is likely to test that to see who really understands this.
Yeah, exactly. This is why we don't include, right, the forces acting on the box. This is why, we remember that third law is saying so the force of A on B, which automatically requires me to consider 2 objects at once. But on those free body diagrams, when I'm doing those calculations, I'm only considering one. So like you were saying, I can't possibly have reactionary forces that meet the criteria for Newton's third law. So I completely agree with you. We're being a little redundant with this, but it's incredibly important to be redundant. It's also helpful to know that you have to be able to break down what directions a given force acts. So the examples that we gave primarily for the first portion, right, the plate on the table on the earth and us on our chair and the chair on the floor, etc. Those were all moving in the same direction. They were fully vertical, either fully up or fully down. But if you think about when you throw a ball in the air, I have never seen someone throw a ball perfectly horizontal, but yeah, sometimes people throw it perfectly vertical, but most of the time it's in kind of like an arch, right?
Yeah.
That means that there's some vertical component and some horizontal component. And for the MCAT, you have to be able to decide what component of a force is vertical and what component of a force is horizontal. And so you need to be aware of vectors for the MCAT. We're not going to sit here and try and show you guys and do some calculations because that would not be good given that it's a podcast. But you definitely want to be able to do that and understand that if, my net movement might be at an angle, but I have 2 components that add up to that movement at an angle. And so essentially it's like a triangle, right? Yeah. Where that vector movement is the hypotenuse and it's made up of the vertical plus the horizontal. And I think if we draw that out, I think that makes sense for a lot of students. So as part of your active studying with the podcast, this is something you're going to want to go and draw a quick little diagram. And if you've already started studying physics and this was a good refresher for you, go ahead and as part of your active studying, take some notes on what we talked about and see how they compare to what you've already written down. And maybe do a practice free body diagram or something along those lines. Sit down and practice the reactionary forces and what forces are acting on a given object.
Yeah, I really like the idea of like talking about vectors. And this is something that you do need to be comfortable with. I always like to use like, not only can one like vector, like movement be kind of like broken up into like multiple directions, but also you could have multiple forces that end up kind of like combining to create a direction that doesn't seem really intuitive. Like if I am like at a river and I'm like, let's say the river flows south. And so it's north going south. And if I get in my boat and I try to paddle straight east, right? I am not gonna go straight east, right? Because the water, my rowing is pushing me east, but the water is flowing south. And so the things acting on the boat, the rowing is pushing it forward, but the water is pushing it south. And so even though I am paddling straight east, there are other forces acting on this. Gravity is pulling it down. And so that's going to make me travel southeast. And so I'm going to go at kind of an angle. And so my actual movement is going to be a combination of multiple forces. The MCAT really likes to take everything we've talked about today, and a lot of times they don't test it just straight by itself. They like to combine it with multiple things, right? Like you may have a magnetic force pushing up on an object and an electric force pushing like to the right on an object, or gravity and like a rope, or buoyancy, but also like a scuba diver swimming to the side, but there's also a buoyant force, right? And that's shoving him to like get him to go kind of at an angle. And so there's lots of different things here that the MCAT can test, that can like combine this with different topics. It's really easy to mix this with a lot of experimental techniques, especially like I know I mentioned about mass spec. There's also like cell sorting stuff that you can do. There's some interesting things you can do with subatomic particles, because like some really interesting questions, just because like alpha particles are positively charged, but they're really heavy. And like beta minus particles are very tiny, but they're negatively charged. And so the forces acting on them and also the differences in mass, like there's a lot of ways that the MCAT can kind of like throw some strange Newtonian stuff at you, where they're going to say like, okay, well, how is it going to be different? One's heavier than the other, but also the charges are different. So if we put up like a positive charge here, it'll repel the alpha particle, but attract the beta minus particle. But the beta minus particle is going to accelerate faster because it's smaller. The smaller mass means a much higher acceleration. And the alpha particle is going to accelerate, be pushed away, but slower because it's heavier. And so like understanding this like attraction, repulsion, but also masses and how it affects things. There's lots of ways for the MCAT to combine it with other stuff. And so Newton's law is something that is really high yield, but I don't think you're likely to see just a straight Newtonian physics question without combining it with anything else. So this is one of those foundational, fundamental ideas that you need to be able to apply to lots of other topics and understand how it mixes with those topics, because that's how the MCAT's likely to test it.
Yeah, this is analogous to the amino acid conversation that we have all of the time, right? So amino acids, single highest yield in the sciences. Newtonian physics, foundational and super important for physics, right? Because like you said, so much of the questions get built off of this. And yes, the amount of questions with ropes used to drive me crazy, or with different pulling forces. But you want to make sure that you have a strong understanding of this before you go forth and go too far into the rest of physics as you're studying.